Hello and welcome to this presentation. I've entitled the higher order differential coefficients. This is the part one of three presentation concerning higher order differential coefficients. The outcome of this presentation are as follows. I'm not going to read through all of them. By the end of this presentation, you should be able to calculate or compute the nth order differential coefficient without doing successive differentiation. I'll explain what I mean by successive differentiation. By differential coefficient, I simply mean something like this, which would be y prime, which will be simply dy dx. We call that a differential coefficient. And in this first case here, we're going to look at two types of functions, which is power functions, that including polynomials, and also we're going to look at the ln function, natural base ln of ax. In this case here, we consider that x is greater than 0. Both a and x are greater than 0. So let's proceed as follows. So we're going to consider the following function, the power function. But before we go deep into that, let's look at the following. Remember, if we're given a function y is equals to x to the power of 4, and we wanted the first order derivative, we'll simply say dy dx, and apply power rule here, which would be 4x to the power of 4 minus 1. And if we were to get the third order derivative, we then had to calculate the first derivative of the first derivative, which will take here as a second order derivative, which will be d2y dx squared equals to, in this case, it will be 3 times 4 multiplied by x to the power 2. And then we'll then go to the third order and then go to the fourth order derivative. That's what I call here finding the first order, the fourth order derivative by successive differentiation, meaning we've got to go through first derivative, second derivative, third derivative, then fourth derivative. So in this discussion, we want to get to a point whereby, given a function as it is, we have a way of computing, let's say, the third order derivative without necessarily going through what I call here successive differentiation. In preparation for that, I think we must understand the following. I hope you understand here that if we need the fourth order derivative of a function y equals to x to the power 4, the answer here is 4 factorial. That is very important to understand. So given any function, any power function of any power, let's say x to the power k, if we were to calculate the derivative of order k, we should also always understand that the answer will be k factorial. That is important for our discussion. So if you want to confirm that, you can check here. We've already got here 3 times 4. If we then to calculate the third derivative here, this third derivative will be 2 times 3 times 4 times x to the power 1. And then when we get to the fourth derivative, we'll get that power 1 here, multiplied by 2, multiplied by 3, multiplied by 4 times x to the power 0, and then which is exactly equals to 4 factorial, since we all know that x here to power 0 is equal to 1. So we've got that is very important. So now, in the discussion which we're going to follow, now we've got to find out that, answer the question that given y equals to x to the power k, how do you immediately compute, without doing successive differentiation, the nth order derivative differential coefficient, which we will denote here as, in other words, dn dy dx to the power n. And here I would like to also emphasize this notation which you saw when you're doing power series expansion of functions. When we go beyond, let's say, the third order derivative, we can comfortably still use the strokes, but after third order, fourth order, sixth order, you normally denote the derivative as y to the power, let's say, 6. Then when you write like that, that power there is not really power, it's an order. It's written like a power, but then with brackets, it indicates an order of a derivative. So it's something different from y to the power 6, which will simply mean y times y dash 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 times y 6 times. So this means order of derivative. So we're going to, you have to get used to this notation by now. So now let's proceed now and look at relook at this experience of using power rule and see how it can lend us to a way of getting to directly to a derivative of order, to differential coefficient of order n without doing successive differentiation. So let's start this way. Let's have y here, prime. Y prime in this case, which you could also write as y1 in brackets there to indicate the order, just to practice this new notation. This will be m multiplied by x to the power m minus 1. And then if we get to the second order derivative, differential coefficient, and then the second order differential coefficient will be m minus 1 times m multiplied by x to the power m minus 2. So we know for a fact that if we were to differentiate this to order m, would get the differential coefficient being y. Differential coefficient order m will be 1 times 2 times 3 times m minus 2 m minus 1 multiplied by m, which is our m factorial. Now what we see here is that we've got the following coefficient, which is m minus 1 times m. So then in other words, if we were to differentiate this m minus 2 times, we know that the derivative of order m minus 2 would actually give us m minus 2 factorial, and this would be 1 times 2 times 3 m minus 2. So now what we can see here is that this derivative of order 2 here, the coefficient which comes here, is actually a result of dividing this m factorial by factorial of m minus 2 and the order there. So what we can see here is that the number which you have here and the number which you have in brackets there, they coincide. So if we follow that kind of a pattern, what we've seen here, if we divide, we'll simply get this simplifying to a 1, and everything here simplified to a 1 up to the end, and then this remains like this. Then what we have there is that the derivative or the differential coefficient of order 2. So what we have here is that the differential coefficient of order 2 is simply m factorial divided by m minus 2 factorial multiplied by x to the power n minus 2. That's what we get there. So we can now generalize this to the differential coefficient of order n. So which means if we follow the same pattern, we would say the differential coefficient of order n will simply be, note that here this comes the factorial of the original power of the expression. The function was given as x to the power y equal to x to the power m, and then that m is the one which brings factorial here, which is m factorial over m minus the order, which is in this case n, in brackets factorial multiplied by x to the power of the same difference here, which is m minus n. So you can see how what this takes us to. So in this case now, if we're just given, let's say for example, we're given y is equals to x to the power 6, and say we need the fourth order differential coefficient. What is this telling us? Is telling us that we're going to have 6 factorial over 6 minus 4, which is going to be 2 factorial multiplied by x to the power 6 minus 4, and then we can see that this simply gives us in the numerator you're going to have 1 times 2 times 3 up to 6 divided by 1 times 2 multiplied by x to the power 2. And now we can simplify this and have that, and then we're going to have here 3 times 4 times 5 times 6 x to the power 2. I'm not going to bother simplifying this, but then you can test that and verify that by differentiating this 4 times, you will see that you get exactly that kind of a derivative. So in conclusion, we must be able to use this even for any type of polynomial. Let's say we've got something like px equals to 7x to the power 8 plus 4 times x to the power 11, and you need the differential coefficient of order 4, then which means you have to apply this kind of approach to each term, and they consider that you're going to multiply by the constant which is already there. The in conclusion is that therefore if you are given a function of a power of x, the nth order differential coefficient will always be given by this formula. So then you can go on and apply this kind of formula to compute your derivative. So then let's move on to the next function. Let's now consider the function y is equal to ln of ax. So I think we already know from a previous experience that if we're given a linear function, let's say f of x, ln of f of x, let's consider here that f of x is greater than 0. So then we know that the first differential coefficient of this function is always 1 over its argument, which is f of x, multiplied by the derivative of its argument. That's the standard formula for getting that derivative. Now, if now we could come to a function like this, we notice that we have got here ln of ax. Now, if we differentiate like this, then we'll say y first order derivative will be 1 over ax multiplied by the derivative of ax, which we know here the derivative will be a. Then this will give us 1 over x, which we can also write as x to the power minus 1. Now, to understand this, again, we're going to experiment, differentiate a number of times just to try to assess what's happening and see how we can come up with a formula like the one we had. So now let's now take the second order derivative, or the second differential coefficient. In this case here, it's going to be minus 1 multiplied by x to the power minus 1 minus 1, which takes us to minus 1. I'll emphasize here that this is minus 1 to the power minus 1 multiplied by x to the power minus 2. If we then continue with to the third differential coefficient, we know what we're going to have here. We're going to have minus 2 multiplied by minus 1 multiplied by x to the power minus 3. And reorganizing this, we can rewrite this as minus 1 multiplied by minus 1 to the power 2 multiplied by 1 times 2 times x to the power minus 3. Now, if we look at that, you can see that we've got a kind of a sequence here. In terms of powers here, we've got, let's start with this one, where we've got the derivative, the differential coefficient of order 1, whereby we've got minus 1 times x to the power minus 1. If you check from these two, this power here and this power there is 1 less than the order of derivative there. And here it's 1 less than 2 there. Now, if you consider that this power here should be 1 less than 1 there, then we should have a 0 here. Now, if we follow that pattern, we see that we've got a pattern of powers here, 0, 1, 2. So if when you get to the fourth order differential coefficient, we are going to be having power minus 4 here, and this minus 1 here would have to be the 3. So I think now we can sort of generalize here. What actually we have here is simply minus 1 to the power 1 less than the order of the derivative there, which is 2, multiplied by 2 factorial, which actually coincides with 2 factorial there and 2 there, multiplied by x to the power minus 3. So taking that to the nth order, following this kind of same pattern here, we would simply get here that the nth order differential coefficient here will be minus 1 to the power n minus 1. I said there, the power of minus 1 here is always 1 less than that of the order. So here 0, 1 less than 1, here 1, 1 less than 2, here 2, 1 less than 3. So now I've got n here, then you should have n minus 1 there, multiplied by n minus 1 factorial. Like you can see here, the power there of minus 1 is the one which we're calculating factorial for, all over x to the power n, because we've got the x to the power minus 3, which will simply give us minus 1 to the power 2 here, 2 factorial, all over x to the power 3. So that will be a kind of a formula which would use to get differential coefficients of order n for a function of this type. So in conclusion, given ln ax, the nth differential coefficient will be given by this formula. Already I've looked at a few isolated examples concerning the power functions and the isolated example concerning the lean function. So what I'm going to encourage you to do now is to do your practice using these exercises. As you can see, you started with the polynomial functions there and the lean functions, and somewhere I'll get the combination of different functions in which you could apply both things we've just learned. And also you mustn't ignore applying the rules of logarithm functions wherever is necessary. At this point, I would like to say thank you for listening. My name is Charles Swaswani MC.